Please pause the video and try this problem. Now we can discuss. Let's start by numbering the carbons, including these carbons. I'm not going to number this carbon, though, to avoid clutter. I don't think I'm likely to make any mistakes with that carbon. Now we need to start trying to assign roles. Well, do you recognize what this group is? I hope you know that this is the general structure of an alkyl sulfonate. So this is an example of an alkyl sulfonate. Remember that alkyl refers to carbon chain. This would be the alkyl group, and this is the sulfonate group. In an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. So over here, the alpha carbon is carbon 1, not this carbon. That's one reason why there was no need to number this carbon. So that would mean that this is the sulfonate group, and this is the alkyl group, a carbon chain connected to a sulfonate group. Well, the important thing about a sulfonate is that the sulfonate group in an alkyl sulfonate is a good leaving group. And in particular, we know that the leaving group atom is this oxygen. Remember that the leaving group atom is the atom that's attached to the alpha carbon. And in an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen, not the carbon attached to the sulfur. So we recognize this molecule as an alkyl sulfonate, a carbon chain attached to a sulfonate group, and we know that the sulfonate group is a good leaving group. I discuss alkyl sulfonates in more detail in the SN2 video series. For our nucleophile, we identify this neutral oxygen in this alcohol as our nucleophile or our base. This neutral oxygen has a lone pair, which makes it want to donate electrons as a nucleophile or as a base. Notice that this is another example of an alcohol, a carbon chain connected to an OH group. This molecule is ethanol, or ethyl alcohol. Now we need to choose our mechanism. Before we can do that, we have to determine that our alpha carbon here is secondary. Always write down what type of alpha carbon you have. You can see from the title of this table that the table is designed to apply not just to alkyl halides, such as we've dealt with in the previous videos in this series, but the table should also apply to an alkyl sulfonate, such as we are dealing with in this problem. With the secondary alpha carbon, we're in the middle row of the table. We're using the neutral oxygen in an alcohol as our nucleophile and base, so that puts us in the left-hand column of the table, and the table predicts SN1 major, E1 minor. So which of those should we draw? Well, look at the instructions. The instructions say draw all possible organic products. That indicates that we need to draw both the SN1 and the E1 mechanisms. Write down that we're going to use both an SN1 and an E1 mechanism. I'm going to start with the SN1 mechanism. The first step is for the leaving group to leave the alpha carbon. Actually, I know that's also the first step for E1. So we draw that first arrow, and now we can draw the products from this step. Notice that first I draw the electron pushing arrow. Only now will I begin drawing the products from this step, following this rule. This arrow tells us to break the bond between carbon 1 and the oxygen, and it also tells us to change the charges on carbon 1 and the oxygen. In our second SN1 step, we need to show the nucleophile joining the alpha carbon. We expect this neutral oxygen to act like a nucleophile now because of its lone pair. Notice that here we're using the oxygen as a nucleophile, not as a base in this step. And we expect carbon 1 to act as an electrophile now because carbons with positive formal charges are good electrophiles. The positive charge makes this carbon want to receive electrons. So here's the electron pushing arrow for that nucleophile electrophile step. Notice again that first we draw the electron pushing arrow Only when the electron pushing arrow is finished should we start trying to draw the products of this step, because the electron pushing arrow is our tool for getting the right products. Notice that I've reminded myself here that this is an SN1 mechanism. Always write down the name of the mechanism, because otherwise it's easy to forget what mechanism you're working on. This arrow tells us to form a bond between this oxygen and carbon 1, which we've shown here. And the arrow tells us to change the charge on the oxygen and carbon 1. Now, the most common mistake on this type of step is forgetting to change the formal charge at the beginning of the arrow. So the most common mistake here would be forgetting to change the charge on this oxygen to positive. The oxygen starts neutral and loses electrons, so make sure that you didn't fall into this mistake. Make sure that you changed this charge to positive. The most important part of your pictures to get right is the formal charges. Another important detail to get correct here is the stereochemistry. The nucleophile in this SN1 mechanism is attacking a trigonal planar carbocation. Since the carbocation is planar or flat, the nucleophile can attack from either in front of the page, giving us retention of the original configuration, or from behind the page, giving us inversion of the original configuration. The stereochemistry here does matter because carbon 1 is going to be a stereocenter in the product. You can see that carbon 1 is attached to 4 different groups. It's connected to this oxygen, it's connected to a hidden hydrogen, and the path around the ring that starts with carbon 6 is a different path than the path that starts with carbon 2. If we move counterclockwise around the ring, we go 2 steps before we get to the methyl group. But if we go clockwise around the ring, we go 1, 2, 3, 4 steps before we get to the methyl group. That counts as 2 different paths or 2 different groups. So this is a stereocenter. So the stereochemistry at our alpha carbon does matter. So we get 2 different stereoisomer products from this step where the nucleophile attacks the trigonal planar carbocation. For full credit, we'll need to include both of these. We'll need to include the products from both of those types of attack in our final answer. On the other hand, notice that there's no reason to change the stereochemistry at carbon 5. Do you see why? Carbon 5 is not participating in the reaction. Nothing is happening to carbon 5, so there's no reason for the stereochemistry at carbon 5 to change. At carbon 1, we will sometimes get retention of configuration and sometimes inversion. But there's no reason for the configuration at carbon 5 ever to invert because carbon 5 is not participating in the reaction. You can see that from the electron pushing arrow. There's no electron pushing arrow involving carbon 5, so there's no reason for carbon 5 to change. The methyl group on carbon 5 was placed here as a trap. The professor has placed this methyl group as a trap, hoping that some students will change the stereochemistry at carbon 5, not realizing that there's no reason to change that stereochemistry. Now you can see why we said here that an SN1 reaction produces inversion at the alpha carbon and retention at the alpha carbon. It's the alpha carbon whose stereochemistry is going to change in the SN1 reaction. If there happen to be other stereocenters in the molecule apart from the alpha carbon, there's no reason for their stereochemistry to change. Notice how we continue numbering this picture to make sure that we're getting the exact right carbon chain. Without numbers, students tend to mess up the carbon chain, but make sure that your numbers are consistent. For example, do you see why this is carbon 9 and not carbon 8? Do you see that this is carbon 9 and not carbon 8? Because in this picture, it was carbon 9, not carbon 8, that was connected to the oxygen. So in this picture, it should be carbon 9, not carbon 8, that's connected to the oxygen. Number all your carbons and make sure your numbers are consistent in your various pictures. That's the way to get the correct carbon skeletons for your answers. Now we can see we're not done because we still have a formal charge on our main product. So we need another step. We need an acid-base cleanup step to clean up this positive charge. So you can see getting this positive charge right really was the most important part of this picture. Without the positive charge, we wouldn't realize that we need another step. In our acid-base cleanup step, the positive charge will make this oxygen act as a strong acid. And we will use another molecule of the alcohol as our weak base. Now we draw the electron pushing arrows for this acid-base cleanup step. Notice that to draw the electron pushing arrows accurately, you have to expand this picture, separate the hydrogen and the oxygen so that you can show the bond between them. I had to erase and redraw so I could show the bond between this hydrogen and this oxygen. I know that's tedious, but that's the only way to really show this mechanism accurately. Let's pause for a second. Why are we using the alcohol as the weak base rather than using this sulfonate group? After all, the sulfonate group has a negative formal charge. Doesn't that make the sulfonate want to donate electrons as a base? Well, normally a negative formal charge would want to donate electrons, but this negative formal charge is highly stable and unreactive. Do you know why? Here's the answer. It's because it's resonance stabilized. The negative formal charge in this sulfonate is resonance stabilized. There are two other resonance structures that can put the negative formal charge on this oxygen or on this oxygen. Because this negative formal charge is spread out between three oxygens, it's highly stable, which means highly unreactive, which means that the sulfonate is a very weak base. So it'll probably be preferable to use the alcohol as the weak base rather than the sulfonate. By the way, that resonance stabilization is also the reason why the sulfonate was a good leaving group. This sulfonate is a good leaving group because it's easy for the sulfonate to leave and gain a negative charge because the negative charge will be resonance stabilized. When the sulfonate leaves, it has to gain a negative charge, but it's easy for a sulfonate to gain a negative charge because that negative charge after leaving will be stabilized by resonance. That's the reason why why a sulfonate group is a good leaving group. Notice that we continued to number. And notice that since I'm using this molecule of the alcohol in a different way than I used this molecule of the alcohol, I've given it different numbers. I didn't reuse my 8 and 9 numbers. I came up with some new numbers. Again, you'll make fewest mistakes if you're careful to number all your carbons. And here it makes the most sense to invent new numbers for this molecule of the alcohol that's been being used differently than the first molecule. Now we can draw the products of this step. Notice that we're not ready to begin drawing the products of the step until we've drawn both of the electron pushing arrows. First we draw both of these electron pushing arrows. Only now should we start drawing the products of step 3, because the electron pushing arrows are our tool for getting the right products. This arrow tells us to draw a bond between the oxygen and the hydrogen and to change the charge on the oxygen from neutral to positive. Students often forget to include this positive formal charge. This arrow tells us to break the bond between the oxygen and the hydrogen and to change the charge on the oxygen from positive to neutral. And it seems that we're now done because our main products now have no formal charge. So that's the end of our SN1 mechanism. Here's our complete SN1 mechanism. We have to make sure that we get these two stereoisomer products, one with retention and one with inversion of configuration. We have to be careful not to change the stereochemistry at carbon 5. When you're drawing the mechanism, you should be careful to get all the formal charges correct, particularly the positive formal charge on this oxygen in this step. We reviewed the idea that a sulfonate group is a good leaving group. Now we need to work through the E1 mechanism. Remember that the first step for E1 is the same as the first step for SN1. The leaving group leaves. We form the same carbocation intermediate from step 1 of the E1 mechanism that we formed for step 1 of the SN1 mechanism. So we don't need to redraw this step. Now in the second step we have to identify our beta carbon. Well, we have two different beta carbons here. Will those beta carbons give us the same product or different products? It should be apparent that these beta carbons will give us two different products because the two beta carbons do have different connectivity. You can see the connectivity is different because, for example, this beta carbon is close to the methyl group and this beta carbon is far from the methyl group. That's enough of a difference to show that they have different connectivity. So notice the connectivity is not based just on what is directly attached to the two carbons. Carbon 6 is directly attached to two carbons and two hydrogens, and carbon 2 is also directly attached to two carbons and two hydrogens, but they still have different connectivity. To describe the connectivity of an atom, you have to describe the complete series. not just of the atoms that the atom is connected to, but of the atoms that those atoms are connected to, etc., for the entire length of the molecule. And if you take that into account, you can see that the connectivity of carbon-6 is different from the connectivity of carbon-2. Carbon-6 is attached to a carbon that's attached to a methyl group. Carbon-2 is attached to a carbon that's attached to a carbon that's attached to a carbon that's attached to a methyl group. That's a difference in connectivity. So we can trust that those two beta carbons will result in different E1 products. So we're going to have to draw an E1 mechanism both for beta carbon 2 and for beta carbon 6. Well, I'll start with beta carbon 6. So I'll erase that beta label for the time being. I should include this sulfonate here because the sulfonate is a product along with the carbocation of the first step. I expect to use the neutral oxygen and the alcohol as the weak base. As the weak base for this step, the lone pair makes it want to donate electrons. And carbon-6 will be giving up its protons, so carbon-6 is the strong acid. It's a strong acid because it's next to this positive formal charge. The positive formal charge makes this molecule eager to receive electrons. I'm going to reuse the same numbers for this alcohol as for this one, even though it's playing a different role in this path. Because this is a completely different path, there's unlikely to be confusion from reusing those numbers. Here are the electron-pushing arrows to show the base taking the beta hydrogen and the pi bond forming between alpha and beta carbons. Notice that, as usual, we had to draw in the hidden hydrogen on this beta carbon to show the mechanism accurately. And notice that we only now will we draw the products of this step. Don't begin drawing the products of the step until you have finished drawing the electron-pushing arrows for that step. Both arrows, because these arrows are the tool we're going to use to get the right products from this step. This arrow tells us to form a bond between this oxygen and this hydrogen. The oxygen started neutral and lost electrons, so it becomes positive. Don't forget that positive formal charge. This arrow tells us to break the bond between the hydrogen and carbon-6 and to form a new pi bond between carbon-6 and carbon-1. Carbon-1 started positive and gained electrons, so carbon-1 becomes neutral. It looks like this is a final product because our main product here has no formal charge. But we have to remember that we have to redo the E1 mechanism now using carbon-2 as the beta carbon. By the way, I should have been more careful to remind myself that this is the E1 mechanism. I should be writing down that this is the path specifically for E1, whereas this was our SN1 path. For this E1, again, we reuse the same first step of the leaving group leaving the alpha carbon. So now we have another branch in the mechanism. We're going to use the same carbocation intermediate as in the previous paths, but now I've labeled that we're going to use carbon-2 as our beta carbon rather than carbon-6. We will use the alcohol oxygen as the weak base again, but now we're going to use beta carbon-2 as our strong acid. Here are the electron-pushing arrows for that step. Again, only now that we've finished both arrows for this step, only now should we start drawing the products for that mechanism step. Draw the arrows for the step, and then draw the products for the step. Because the arrows are the tool that we use to figure out the correct products. This arrow tells us to form a bond between the oxygen and this hydrogen. The oxygen started neutral and lost electrons, so the oxygen becomes positive. This arrow tells us to break the bond between carbon-2 and the hydrogen and form a new bond between carbon-1 and carbon-2. Carbon-1 started positive and gained electrons, so carbon-1 changes from positive to neutral. Remember, you've probably noticed that so far I've usually been not just drawing the products, but trying to explain how the electron-pushing arrows tell us how to draw the products. And I hope that you've been thinking about that when you're drawing these mechanisms on your own. Don't draw the product that you expect to see, or that you've memorized that you should see, or that you guess you should see. Try to use the electron-pushing arrows as a tool to make sure that you're going to draw the correct products. That gives you the way to develop your OChem insight, to avoid having to just rely on memory, and it also will make you more flexible, so that if the professor gives you a problem that's a little bit different than usual, you'll be able to use the electron-pushing arrows to figure out how the product is a little bit different than usual. So by using the two different beta carbons, we expected to get two different alkene products. And I hope that you will agree that these two products are obviously different. These are obviously different molecules. For example, in this product, the double bond is one step away from the methyl group, whereas in this product, the double bond is two steps away from the methyl group. So clearly these are different products. We expected them to be different products because the two beta carbons have different connectivity. But remember, to see that they have different connectivity, it's not good enough just to look at the 4 atoms that are directly connected to the beta carbons. You have to think about the complete series of atoms that the atom is connected to through the entire length of the molecule. For example, carbon 6 is connected to a carbon that's connected to a methyl group, whereas carbon 2 is connected to a carbon that's connected to a carbon that's connected to a carbon that's connected to a methyl group. That's a series of atoms, and since those two series were different, we can see that those two atoms have different connectivity, and we can trust that they'll give us two different products. And then we can confirm that the two alkene products really are different when we've finished drawing them, as we have here. So here is our complete answer. Remember that for full credit, you would not actually have to draw this complete mechanism, because the problem didn't mention the mechanism. For full credit, you just have to draw all the products. But I do encourage you to keep drawing the mechanisms at least a little while longer to develop your OChem skills. And notice that when you do draw mechanisms, don't cut corners. For example, it would be tempting, instead of drawing all these different branches, it would be tempting to try to draw two different mechanisms on the same picture. For example, it might be tempting to try to smush these two pictures together and show the attack on this beta hydrogen and show the attack on this beta hydrogen in the same picture. But I advise against that. That's just going to lead to confusion. Instead, we drew separate pictures. One picture to show the attack on this beta hydrogen and a separate picture to show the attack on this beta hydrogen. Technically, this problem said that you needed to draw all possible organic products. Notice that in this case, technically, all the products are organic because they all have at least one carbon. This has carbons, 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 this is carbons. Technically, even this is organic because it has one carbon. So technically, this is a product, 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 and of course, this is a product. So technically, we've got 1, 2, 3, 4, 5, 6 different organic products here. Professor might not care about whether you include this in your products. Obviously, the most interesting products here are the ones with the ring, but you probably should include this product and this product as well if they're asking for organic products. Again, I know that when you take your exam, there might well not be enough time to completely draw such a careful mechanism with all these different paths and branching, but it is good to practice this type of mechanism on your own. And when you're taking the exam, you might still find it helpful to draw a somewhat abbreviated version of this mechanism, because again, the mechanisms are our tools for figuring out the products. Remember that this problem gave us a chance to practice using an alkyl sulfonate. The sulfonate is a good leaving group, and it can be used as a leaving group for SN1 or for E1. For that matter, you could also use a sulfonate for SN2 or E2. I think this is the first problem where we used ethyl alcohol as our nucleophile and base. So notice how we handled that, making sure to get the exact right carbon chain in our SN1 products. In our SN1 products, we had to show retention and inversion of configuration at carbon 1, but there was no reason to make any change in the stereochemistry at carbon 5, because carbon 5 is not participating in the mechanism. Now, I'd like to work through one more exercise in this video. Let's go back to our SN1 mechanism, and let's consider an alternative step 3 for the SN1 mechanism. This is a different way we could have drawn the arrows for step 3 of the SN1 mechanism, and I'd like you to decide whether these would have been reasonable or unreasonable electron pushing arrows. decide whether this set of electron-pushing arrows should be considered reasonable or unreasonable electron-pushing arrows, and try to give a simple reason why for your answer. I hope you actually paused the video and thought about that. These are unreasonable arrows for a very simple reason. These arrows are unreasonable, and you can easily see that because the series of arrows begins on a positive formal charge. Can you see how unreasonable that is? If something has a positive formal charge, it wants to receive electrons, not donate electrons, right? Remember that an electron has a negative formal charge. Well, something that's positive wants to receive negatives, not get rid of negatives. These arrows are clearly unreasonable because they begin on a positive formal charge. Electron-pushing arrows should end, when possible, on positive charges, not begin on positive charges. That should be obvious, but I oftentimes see students write electron-pushing arrows like this because they say that the oxygen can donate electrons because of its lone pair. Well, it's true that this oxygen does have a lone pair, but that's not going to make it want to donate electrons because the positive formal charge is more important than the lone pair, so to speak. The positive formal charge overrides the lone pair, so to speak. If you see a neutral atom with a lone pair, it might want to donate electrons, and definitely a negative atom with a lone pair would want to donate electrons. But if an atom has a positive formal charge, it definitely does not want to donate electrons, even if it has a lone pair. This example of bad electron-pushing arrows illustrates that the most important factor in organic chemistry is the formal charges, because the formal charges are your most important tool for drawing reasonable electron-pushing arrows. Here are the rules for using formal charges to draw reasonable electron-pushing arrows. At the beginning of a series of arrows, you should put either a negative formal charge or a neutral formal charge. You should never put a positive formal charge at the beginning of the series of arrows, because something with a positive formal charge wants to receive electrons, not donate electrons. That's the reason that these arrows were bad. These were bad, unreasonable arrows because they put a positive formal charge at the beginning of the series of arrows. But that's the position where we want to put a negative or a neutral formal charge, never a positive formal charge. We should put a positive formal charge at the end of the series of arrows. Or sometimes you might need to put a neutral formal charge at the end of a series of arrows. You would never put a negative formal charge at the end of a series of arrows. And we almost always want to put neutral atoms in the middle of a series of arrows. We almost never put a positive or a negative formal charge in the middle of the series of arrows. These are the rules for using formal charges to draw reasonable electron-pushing arrows. So remember that the correct way to draw the electron-pushing arrows for step 3 of the SN1 was like this. These were the good arrows. All the examples on this screen are examples of good, reasonable arrows. Notice that in this case, the positive formal charge is at the end of the series of arrows. We want to put a positive formal charge when possible at the end of the series of arrows because an atom with a positive formal charge wants to receive electrons. So notice, for example, in this step, the positive formal charge went at the end of the arrow. Then in this step, the positive formal charge went at the end of the series of arrows. In this step, carbon-1 is receiving electrons at the end of this series of arrows, and that makes sense because carbon-1 has the positive formal charge. Again, in this step, carbon-1 is receiving electrons at the end of the series of arrows, which makes sense because carbon-1 has the positive formal charge. So in most of these examples, we were able to put a positive formal charge at the end of the series of arrows. In the first step, we didn't put a positive formal charge at the end of the series of arrows, but we did put a neutral atom at the end of the series of arrows. At the end of the series of arrows, you should put something positive or something neutral, never something negative. In all of these examples, we put something neutral at the beginning of the series of arrows. Something neutral at the beginning, something neutral at the beginning, something neutral at the beginning, something neutral at the beginning of the series of arrows. At the beginning of the series of arrows, you want to put something negative or something neutral. Notice that in these examples, we never put a positive atom at the beginning of the series of arrows, because a positive atom doesn't want to donate electrons. It wants to receive electrons. To draw reasonable electron-pushing arrows, put something negative or neutral at the beginning of the series of arrows, never something positive. Put something positive or neutral at the end of the series of arrows, never something negative. And put something neutral in the middle of the series of arrows, almost never something positive or negative. The most important factor in organic chemistry is the formal charges, because the formal charges are your most important tool for drawing reasonable electron-pushing arrows. Be especially careful to avoid this mistake of putting something positive at the beginning of a series of arrows just because it has a lone pair. When a neutral or negative atom has a lone pair, the lone pair makes it want to donate electrons. But when a positive atom has a lone pair, the positive charge is more important than the lone pair. The positive charge makes this atom want to receive electrons, not donate electrons. So the positive charge makes this atom want to go at the end of the series of arrows, not at the beginning of the series of arrows, even though it has a lone pair. So again, these would be an example of bad, unreasonable arrows. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.